Okay, good. For those of you who came in a little late, it was quite an effort yesterday. I spent most of the afternoon with Yaman on Zoom trying to make everything work and merging. We had 7 pieces of yesterday's lecture. It only recorded 17 to 18 minutes at a time, but then immediately record the next one, and there was sophomore that we merged it into one, and then when we went to download it from my super slow speeds at home, it was going to be, well, we estimated 16 hours. We estimated, because after 15 minutes it hadn't reached 1% downloading yet. So today we went and did this from my office, where the download speed here, I'm not exaggerating, was almost, or the upload speed is almost 300 times what it was in my house. It was almost 1,000. Mine, it was 3 at home. So the entire 22 gigabyte, I've never seen anything that big in my life, by the way. I've never seen anything bigger than 8. 22 gigs, it downloaded to YouTube in like 10 minutes. Now it's processing. So I'm doing the happy dance, jumping up and down in my office. Now, we're just gonna see how well it works. I've already put it on Canvas, although I don't think you can get to it yet because it's not done processing. So later on, if anybody, you want to just spend 5 minutes, just click on it, look at it, and give me feedback on what you see from your end. Because I have the video, so I don't know what you guys would see necessarily exactly the same way. And if it works, we'll keep this going. And I love this because, see, now I have records for future classes as well. So it's a good thing. It's all good. We're going to start today. We're going to invent 2 forms of multiplication. And I mean invent because vectors can be added and they can be lengthened or shortened. And that's basically all you can do with a vector. But we want to make them useful tools. So we're going to define 2 types of multiplication. And this is one of the most important parts of the entire vector world, is understanding the differences. When working with vectors, the result of your answer is either going to be a vector or it's going to be a scalar. There's no ambiguity, there's no gray area, and messing that up is a major thing. In other words, when your answer is supposed to be a scalar and you give a vector, or your answer is supposed to be a vector and you give a scalar, you know, all hell breaks loose. Dogs sleeping with cats, you know, world comes unglued. Does that happen? Yes, actually a high percentage of the time people get confused and they do something else. In Calc 1, it'd be kind of like saying, I want the integral and you took the derivative. You did a correct operation, but you did something completely different, and you know it wasn't going to work. So we're going to define dot product first of all. And then we're going to get into why and the uses of dot product, because dot product is extremely important in the math realm, and it's also important in the physics realm, but we have to define it first. So dot product, first rule is your vectors have to be the same dimension. So I'm going to give you the general rules that apply always, and then we'll break it down to the specifics, because we're never going to work with vectors other than 2 and 3 dimensions in this class. But the rules for dot product apply to all dimensions. So we're going to say n-dimensional vectors. So I'm going to have vector u and vector v be elements of Rn. That means then that vector u is u1, u2, dot, 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 un. There are n components. It doesn't matter how big n is. The only thing that matters is that both of these have the exact same number of components. Okay? So I'm giving you 2 n-dimensional vectors, knowing, again, for this class it's going to be 2 or 3 most of the time, but understand, in other math classes you're going to be dealing with higher dimensions. A lot of times we get confused by the term dimension, because we always think about it from a geometric point of view. Okay? Dimension is simply determined by how many of these there are. You have worked with multidimensional things in the past and you may not have even realized it, so we're going to talk about that stuff in a bit. So with that, u dot v is defined to be the sum from I equal 1 to n of ui vi, which I'll expand in a moment. This is the definition for real valued vectors. I said they are in Rn. What that means is that every component is a real number. Is it possible that the components are complex? Yes. In a higher level math class, you would consider that. And the rules change slightly, by the way. If you're dealing with complex vectors, the rules are a little bit different, and that definition has to be tweaked a bit because of the imaginary numbers that might be in there. You're not going to deal with any imaginary numbers in this course. So this is the definition for real valued vectors. So what is this? Well, this is u1 v1 plus u2 v2 plus all the way to un vn. So what I'm doing is taking this product plus all the way down the line, finishing with the last one. This is a real number. This is a scalar. Okay, this is not a vector answer. So a dot product produces a scalar. Now, this is the definition. So what the heck's it good for? Well, we're going to go into that in a moment. But this is the, not a definition, but the definition. This is notation out of convenience. A lot of people see this and they kind of cringe. Well, it's an easier way of saying this. So if I only had vectors in R2, let's say. So let's say my u was 3, 5, and v is -2, 6. Then u dot v is equal to 3 times -2 plus 5 times 6. It's actually that simple. Okay, piece of cake. Now let's go back to the definition. The u's and the v's are real numbers. So u1 times v1 is a product of real numbers. But I know something about real number multiplication. Isn't it commutative? I mean, we know this. Why does that matter? Because that means that this equals v1 u1 plus v2 u2 all the way down to vn un. And that is v dot u by definition. This is an extremely powerful conclusion, and it's also really cool. It means dot product is commutative. Dot product of real vectors is commutative. If they're complex, not quite so. But we're not going to be doing anything complex. So if I went back to this problem here and you said, well, what's v dot u? Oh, I'd get the same numbers, wouldn't I? Because I'm multiplying, it doesn't matter what order I multiply. That's a nice thing. So dot product is commutative. The only rules on dot product is your vectors have to be the same dimension. That's it. And your result is a scalar, so it didn't matter what dimension you started with. Okay? So with that said, we'd like a geometric interpretation of this. You know, we talk about things like, you know, work being dot product. Well, how does that figure in? Because that doesn't look anything like this. When I talked about pushing the refrigerator across the room, there's a dot product somewhere in there, but I don't see it yet. Now, here's the other thing. This is only relative to an xy, xyz, or, you know, some coordinate system. And I say this tongue-in-cheek, but all the time, we're going to be dealing in 3 dimensions most of the time. Most of our vectors are in R3. And so we're going to write vectors that look like that. Problem is, when you go outside, right, I'm hard-pressed to find the x, y, and z axes when I go outside. You know, you're out there going, okay, this looks kind of like the x-axis and the y-axis and the z-axis. Meaning, when you go outside, vectors will never look like this. No, it'll be go that way 100 feet. That's your vector. I gave you the direction, I gave you the length. And that has perfect meaning to us once we walk outside. When I walk outside, there is no coordinate system. So that means all the time you work with vectors, there's really going to be 2 representations. The easy one, the one that I can do pencil and paper because it's based on a coordinate system that I can apply it to, or when I go out in the real world, it's no, go this direction, this distance. There is no coordinate system. Okay? When that plane is flying through the air, you know, and the pilot's trying to figure out where they're, you know, there's a really tall z-axis, right, that they can always, you know, look at to figure out their altitude and stuff like that. We all know that. You've all looked outside the plane and seen the axis, right? or maybe not. So now let's look at the geometry. So I'm going to do something that you learned a million years ago in trig. All right? There's a relationship between A, B, C, and theta. Does anyone remember what the name of it is? There's a law. Cosines? Law of cosines. I don't care if you remember what the law of cosines is, but there was something called the law of cosines, that if I have these 4 values, Or if I have 3 of the 4 values, I can always find the other value. And the law of cosines was something like this. C squared equaled a squared plus b squared minus 2ab cos theta. This is always true for all triangles. There was something called law of sines, which means I have to have different information. In law of sines, there's going to be 2 angles involved. But law of sines is less useful for finding missing pieces because if you have an acute triangle, you'll get an answer. If you have an obtuse triangle, you'll get an answer, and one of them will be contradictory. Why? Because the sine of the second quadrant angle is the same as the sine of its supplement in the first quadrant. Oh, but in cosine, a first quadrant angle, I have a positive value for the cosine. A second quadrant angle, I have a negative value. All answers are unique. And what if theta happens to be 90 degrees? Then what's the cosine of theta? Cosine of 90 degrees. 0, which means that I would have the Pythagorean theorem. The Pythagorean theorem is a natural consequence of the law of cosines if I have a right angle. And by the way, is that a good thing? Yeah, it's kind of, okay. It didn't all of a sudden mess up. So why am I showing you this? Well, what if I replace the a and b with vectors? I'm going to give you a little bit of notation you may or may not have seen before. Okay, let's call that vector u. Let's call that vector v. If I took the negative of vector v, which would be a vector pointing this way, and then I added it to vector u. Then I would get this vector here. Do you agree? So why don't I just put it right there? Same vector, isn't it? I'm just moving it up there. So I know if I added u and v, I just take one vector and glue it to the end of the other vector, and then it didn't matter what order I added them. But I'm taking the negative of vector v. So in other words, I'm technically subtracting vectors here. So what, the hat is here. So what is technically this vector? It would be u minus v. So that's what it would look like. Okay, everybody with me so far? What if I did v minus u? Well, it's the same vector, just pointed the other direction. I am interested in the triangle that I just formed. So I'm not interested in the vectors so much as their magnitudes. Okay? And because I'm interested in their magnitudes, would it really matter what order I subtracted, by the way? No. So the magnitude of u minus v, there's a symbol that we often use, du comma v. That's a little confusing. How many have ever seen that symbol before? Do you remember what it meant? It's basically distance. It's literally the distance between the tips of u and v. Oh, okay. If I said how long is this vector right here, isn't that exactly the distance from the terminal points of u and v? So that's why we often call it duv. Okay. The magnitude of that difference is exactly that distance. And would it matter what order I subtracted at that point? Not at all. Okay? So what I want to do then, I want to go back to this picture here, but instead of A, B, and C, why don't I call it, I don't know, magnitude of U, magnitude of V, and then what would this one be? Magnitude of U minus V. Does everyone see that's the same thing now? I've created a triangle, not a right triangle. I've created a triangle, I've got that angle. I know for a fact the law of cosines now can be applied to this. So the law of cosines says that the magnitude of u minus v squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u, magnitude of v, cosine theta. That's absolutely true. Okay? Again, when we go outside, there's no coordinate system. So I really have to describe vectors in terms of their magnitudes and directions. Unless we went outside and said, here's the origin. There would actually have to be an origin outside, wouldn't there, to to apply axes and things. Probably not very useful. Now, let me make up a u and a v. I'm going to do this in 2 dimensions, and then I'm going to show you that it extends to 3, and then I'm going to show you that it extends to n. But it's easier if I start with 2 because the algebra. So let's start with vector u being u1, u2, and vector v being v1, v2. Okay? Then what would vector u minus v be? That would be u1 minus v1, u2 minus v2. Okay, we all agree with that? I need these magnitudes. So but I don't want the square roots because you notice most of those are squares. That's a good thing. So with that said, what is the magnitude of u squared? Well, wouldn't that be u1 squared plus u2 squared? Yes? And then the magnitude of v squared would be v1 squared plus v2 squared. And finally, the magnitude of u minus v squared would be u1 minus v1 squared plus u2 minus v2 squared. Okay, great. Boy, this makes for a really messy set of equations, but let's do it. Let's take these and substitute them into here. The only difference is when I go to 3D, the only difference that I'm going to show you in a moment was that I'd have a u3 squared, a v3 squared, and a different square. Everybody see that? And if I go to 4, I just keep adding the same form, but I just keep adding new terms down the road. For the sake of the algebra, I start with this, I show you the extension, and what I prove for 2 will actually be true in all dimensions. So let's put these numbers in. So on the left side, I've got this. I'm going to go ahead and expand this, because clearly there's going to be some canceling going on. So I'm going to have u1 squared minus 2u1v1 plus v1 squared plus u2 squared minus 2u2v2 plus v2 squared. Okay, that's the left side. The right side, u1 squared plus u2 squared plus v1 squared plus v2 squared plus, or sorry, minus, and I'll just leave it like this for now. I'm going to leave those right there for now, because right now they'd just be icky square roots, wouldn't they? And I don't really want to write the square roots yet. Times the cosine of theta. Okay. Now, do you see anything going on here? Hopefully you do. All the squared terms are going to cancel, aren't they? Boom, 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 boom. And again, if I had had a third term, there would have been a u3 squared and a v3 squared over here, but there would have also been a u2 squared and a or u3 and v3 squared over here. They would have still canceled. What's left now? Well, on the left side, I've got this and this. So I've got negative 2u1v1 minus 2u2v2 equals negative 2u v cos theta. Okay, this is true. Okay, I haven't done anything. This is true just based on what we already know about magnitudes and law of cosines. This is not even about vectors at this point. This is about stuff we already know. Every single thing has a coefficient of negative 2. Huh. How about if I multiply both sides by negative a half to get rid of those guys? Then the left side will be u1v1 plus u2v2, and the right side will simply be length u, length v, cos theta. Okay, great. Anybody getting an overwhelming sense of deja vu here? What is that? That is the dot product, isn't it? That's the definition of the dot product. Ooh. U dot v equals length u, length v, cos theta. Importance? Probably top 10. Like everything math. That's huge. Remember I said when you go outside there's no coordinate system. It's go that way this far, go that way this far. Your vectors are only going to be magnitudes and directions. We have just proved that dot product, which we defined to just be this simple thing. If I give you vectors in this form and I say dot product, you multiply and add. That's trivial. It doesn't, that in itself doesn't really seem to have application. That's just what I do. But I just proved it's the same as saying the magnitude of this guy times the magnitude of this guy times the cosine of the angle between them. Whoa. And this is true in all dimensions because I'm going to do a what if. I'm going to squeeze a U3 and a V3 in here, and then here I'm going to squeeze a U3 minus V3. So then what happens? Plus U3 squared plus V3 squared plus U3 minus V3 squared. And then over here I need a different color. Then what happens over here? Well, now I have a U3 squared minus 2U3 V3 plus V3 squared. And on the right side I have a U3 squared and I have a V3 squared, and then that cancels, that cancels, that cancels, that cancels, and I have a negative 2U3 V3. All right, Captain America says, I can do this all day. Does everybody see that it wouldn't matter how many times you do this, it's always going to work forever and ever and ever? This is dimensionless. This is always true. Cool. Now, what if U and V were at right angles? Then the dot product would be zero, which is the simplest test there is to determine if vectors are orthogonal. Ooh. If the dot product is zero, they're at right angles. They are orthogonal to each other. That's really handy, isn't it? What if theta is an obtuse angle? If theta is obtuse, then the cosine is, starts with an N,
Negative.
ends with a negative, good. So that would mean my dot product is negative. The most common and useful example of dot product is work. And we talked about this yesterday. Now I can give it a little more idea. I'm going to apply a force in this direction. I want to move my refrigerator in this direction. And I actually go in this direction. So I'm dotting the force with the displacement. Force is force units, displacement is length units. And I'm pushing in the same direction. So when you were kids in physics and algebra and different things, if someone says, what's work? Didn't you always say force times distance? And we go, that's the easiest one. Well, yes and no. It's force times distance if you're pushing it in the same direction that you are measuring the work. Oh, it's force times distance if I said, what's the work done in the direction that I'm actually applying? That's easy. The displacement, so the magnitude of force, the magnitude of displacement, and the cosine of 0 would be 1. Okay, so now I'm going to push it, but something decided to tilt the room a bit. So when I'm pushing it, I go off, let's say, at a 45-degree angle. So when I go off at a 45-degree angle, maybe I pushed it to where Liam's sitting. Do I get full credit for my displacement in that direction? No. Oop, hold on a second. So the idea being, I want to go that way, I pushed it that way. I don't multiply that length by that length. I only get this much of it, don't I? And how much is that? It's a SOHCAHTOA thing. It's this length times the cosine of theta. Okay, so I want to push, and I start pushing, and I go sideways, and I push it a great distance sideways. So how much work did I get done pushing it across the room? 0. I'm no closer to the other side of the room. But now that's exactly using this, isn't it? Now the concept of negative work always throws people. I always have fun with this one. Hopefully this has never happened to you, but maybe you got to watch it. It's hysterical. Somebody's run out of gas or something's going on, and the car is parked facing the uphill. And the person in the, inside the car, and the person, you're ready to push it, okay, take your foot off the brake. And what does the car do? It starts rolling backwards. Or worse, I've seen people get their car behind the car and they were going to push it. But the problem was they let a little gap create, and now all of a sudden it's the funniest thing I've ever seen, but I've seen it before, and usually you figure out really quickly that's not going to work. I want to push it in that direction, and I ended up going this way. 180 degrees. -1. I got negative work done. And the concept of negative work, a lot of people think, no, that's not possible. No, actually, it's very possible. Think of it this way. I want to push the refrigerator this way, and I roll backwards. I now have to perform a positive amount of work just to get back to the starting point. That's why negative work was done. Does that make sense? Because you add the amount of work done. Those who've had physics, you guys have done all the things with the pulleys, that's like the most evil problem. It's just there to mess you up. It's like putting you in a maze and asking you to find the cheese. But the idea is you've got all of these things and you add everything up at some point. So the concept, again, I like using this example and work because it's the simplest example and probably the most useful example of dot product. And in fact, pretty much every time we do anything that's involving dot product, our result is going to be work because that's the whole intention of this. So length, cosine theta. So when I say, okay, Will, go outside and push in a general this way, this far, with this much, there's no coordinate system, so you're going to be measuring your dot product this way. But the ability to go back and forth. So I have a simple question. What if I know this, I know this, I know this, I just want to find the angle. Can I find the angle? What's the cosine of theta? Well, that's going to be u dot v over the magnitudes. Let's assume, by the way, that neither one of these vectors is the zero vector. That just kind of messes everything up. The zero vector is the vector of zeros. And the vector of zeros is automatically orthogonal to all vectors. Why? Because when you do the dot product, you always get 0. So therefore, theta is just simply the inverse cosine. This is one of the simpler calculations to perform. Now, the question always comes up, what is a better answer in terms of units? Because everybody knows radians are a measurement. They are actually a measurement. They have meaning. Degrees are actually a made-up term. Degrees have no meaning in and of themselves. We apply meaning to them. Degrees, I say, they're a descriptive term. If you were finding the circumference of a circle, you can't use degrees, you got to use radians, right? It's 2 times pi, which is the arc length all the way around, times the radius. Because that's what arc length is. In a circle, arc length is the angle in radians multiplied by the radius. So you can't say 360 degrees times the radius, that's meaningless. But if I said, all right, Joseph, could you open the door about, 0.372 radians? That would be kind of weird, wouldn't it? But if I said, can you open the door, roughly 45 degrees or something? You go, piece of cake. We use degrees to describe something. We use the radians in calculation. So if I said, what's the angle between the two vectors? What do you think is a more useful answer, radians or degrees? Degrees, because you're not actually going to use that for anything else. You're describing the angle between two things. So a degree answer is probably far more useful because conceptually. Here's the other reason. If I gave you a radian number, just in general, do you automatically know whether it's obtuse or acute? Yeah, so mistakes can be made because I don't recognize the radian answer. Remember, if the dot product is negative, then the angle is obtuse. And if I use degrees, that means the angle is going to be between 90 and 180 degrees. And that's a really quick check that I did it right. Oh. But if I give you a radian answer, I don't know about you guys, but I can't convert, a degree answer to radians in my head that fast. It might take me a couple minutes. I mean, if you saw 3.14 something, you'd probably recognize, okay, that's pi. And of course, everybody would know pi over 3, or pi over 6, and pi over 4, or pi over 2 off the top of their head. Or what about it, just an odd, 37.9 degrees? Well, you're going to get some icky number. There's no right or wrong answer. I think degrees are more useful when you're describing the angle. And here's the thing, it doesn't matter what dimension you're in. Whoa, that's crazy. Now, there's a word that I've used already a couple times, and I strategically use it, and I need this to be part of your regular vocabulary. It's the word orthogonal. This is a really, really important math word, geometric word. Those who've had linear algebra, you know this word inside and out. And in the linear algebra, it is synonymous with another word. What word? Perpendicular, because in linear algebra, there's nothing curvy, everything's, well, linear, that's why it's called linear algebra. But if something's perpendicular, it's orthogonal. But orthogonal doesn't necessarily mean perpendicular in reverse. It's a much bigger term. So I'm going to give you a simple example, because I use words like orthogonal all the time. The word perpendicular, what does it mean for things to be perpendicular? Look around the room. Do you see examples of perpendicular? Look at the ceiling. Do you see it all over the place? How about the walls and the floor? You see lines that are perpendicular. You see planes that are perpendicular. Perpendicular, first of all, only applies in 2 or 3 dimensions. Orthogonal applies in all, so that's one major difference. To be perpendicular means things must meet at right angles. That's the definition of perpendicular. But the things have to be straight. So perpendicular only applies to lines and planes. I've got a curve. I've got another curve. You cannot measure the angle between curves. That's not physically possible. But what could you measure the angle between?
Tangent lines.
Tangent lines. Beautiful. Some of you have attended my classes before and you paid attention. If those tangent lines are perpendicular, then we say the curves are orthogonal. So you see, that's why orthogonal is a little more useful. The curves can't meet at a right angle. There's no angle to measure on a curve. Okay? But I can measure the angle between tangent lines. Think of a basketball. Now imagine from the center of the basketball, you went straight out. Anybody who's ever pumped a basketball, you pump it straight in. Imagine from the center of the basketball, there was something going out of the basketball. So you've got this thing going out, the top of the basketball. I can put a tangent plane. I can take a piece of cardboard and set it on the basketball, and it would be a tangent plane to the basketball. This thing coming out of the center of the basketball should be orthogonal to that piece of cardboard, shouldn't it? Okay? So we would say this line coming out is orthogonal to the surface of the basketball. Okay? If I'm standing with good posture, am I making a right angle with the floor? Yeah, but that's easy. The floor is plane. So go outside on the grass or on the dirt. You're now on the surface of more or less a sphere, a really big sphere. You technically can't be at a right angle with the sphere, but can you still be orthogonal to the surface of the earth? Yes, because now you're thinking of the tangent plane. This is correct mathematical. Orthogonal applies in all dimensions. We generally don't use perpendicular in all dimensions. The terms perpendicular and parallel, we were conditioned as babies in algebra to always apply them to lines. In fact, it was hard to get people just to think of planes, right? Those walls are parallel planes. The floor and the ceiling are parallel planes. In fact, the lines running along the ceiling and the floor are parallel. I have lines parallel to this plane. That's okay. We're all right with that. But we're conditioned to think of perpendicular and parallel only as they apply to lines and planes. Parallel, you don't even have to be straight. The definition of parallel does not in any way even reference lines. In baby algebra, 2 parallel lines on the plane, that's where we started. You live in 3D. I mean, you don't have to be lines on a plane. So when I ask, what is the definition of parallel, do you know the number one response I get? 2 lines that don't intersect. Now that's interesting, because if I take any line running along the ceiling and I take any line running along the floor, they're never going to intersect, and there's a 1 in infinity chance that they're actually parallel. No, the probability of that being true is actually 0. It's literally of an infinite number of possibilities that would only be true in one of them. No, those are called skew. Think of flight patterns of an airplane. This is not a joke. People always laugh when I say this. Think of flight patterns. All flight patterns from any airport must be non-intersecting. Think about that. Flight patterns, if flight patterns were parallel, that means they're all going to the same destination, aren't we? No, it's this. The definition of parallel is threefold. Non-intersecting is key, because if you said same direction only, couldn't it be the same line? Oh, that's concurrent. So non-intersecting, same direction, equidistant. If any 2 of those 3 are correct, you have parallel. Where in there does it mention lines or straight or anything? No. Did anybody drive here today on the freeway? Did you experience parallel? Gotta hope so, because if you didn't, you probably wouldn't have made it. But you didn't drive on a line, you drove turning. Where's the parallel? Your lanes. Railroad tracks are parallel. How do you know? Well, they're not intersecting. That would be really bad for the train. They're equidistant, because again, that would be really bad for the train. And what else? They're going in the same direction. Oh, okay. So the traffic lanes, the train tracks, those are perfect examples of parallel. Now, by the way, what happens if they're straight? Well, that makes it even easier, but do they have to be straight? No, they do not. We're going to be dealing with things that are parallel. We're going to be talking about surfaces. Oh, what if I had two concentric circles? Keep it simple. Concentric circles mean circles with the same center. So imagine you had two concentric circles of different radii. Then would the outer portions of the circles be parallel? Yes, they would. Whoa, an inner circle and outer circle are, yeah, it perfectly fits. So I could do the same thing with spheres, concentric spheres. Now, I'm trying to broaden your mind a little bit so that you don't put your own biases on things and therefore say, no, I can't do this, when actually you probably can do this. There's so many things you'll be able to do in this class that you did not realize. Because when we open things up to 3 dimensions and we use our 2-dimensional definitions and say, how do they apply in 3, it usually makes things less difficult. What was your most hated type of derivative in Calc 1? Everybody has the same answer. Started with an I, M, P.
Improper integral.
Remember implicit differentiation? Oh, yeah. You had things that were not functions, circles, figure out, and you had to find derivatives. Implicit differentiation was gnarly. Nobody goes, oh boy, we have to do implicit today. After we get done with doing derivatives in this class, you guys are going to love implicit differentiation. You're going to invite it to a party with you. It's going to be your friend, because you're going to say, this is so easy. Because there's everything in 2 dimensions. And by the way, I'm going to prove this later, because this is part of the point of this course. Everything in 2 dimensions comes from something in 3. Everything in 2 dimensions is a slice of something in 3. Therefore, everything in 2 dimensions that was not a function is actually a function in 3D. All circles you're going to see as functions. I'm going to give you a glimpse because this is where this class is headed, and I need you on board to understand, because the thinking is totally different. One of my favorite shapes to deal with, because I can actually draw it, is this one. It's called a circular paraboloid. And something like this. Z equals x squared plus y squared. Okay? It's called a circular paraboloid. Don't worry about that. We're going to get into surfaces later. If I said, I want you to slice this parallel to the xy plane. Now remember, the z is going up. We'll get used to this in time. This is coming out of the board. So if I said, let's just take an arbitrary slice. What does that slice look like? It's a circle. Meaning all circles that exist. Let's say circles centered at the origin, just to make it easier. All circles centered at the origin are a slice of this. It's called a level curve. We'll get to that term later. But all circles are just a slice of this. This is a 3-dimensional function that's actually very simple to work with. All circles are simply a slice of this. You can't have a circle that didn't come from this. So if I'm looking at circles and go, boy, circles are so hard to work with, then let me step back and look at it as a 3-dimensional problem. And if I take everything 2-dimensional and realize it's just a slice of something in 3, then the calculus actually becomes much simpler, not harder. 100% of the time, it'll actually make things easier. But you're looking from things from a different point of view. You did all of math with one eye closed. And I don't say that jokingly. You did all math your whole life in 2 dimensions. But that's very restrictive. When you do it in 3, a lot of the rules are gone. And it makes it much, much simpler. Okay? So dot product applies in all dimensions. For this class, we'll only be doing it in 2 and 3 because we're only going to be doing essentially the physics of calculus. And I use that word with caution. We're not going to do physics like a physics class, but all the things we do are applications of the physics. We just don't dwell on the units and things, but we need to know where things are coming from, okay? So with that, dot product becomes a fairly simple notion. So let's do a really simple example, all right? I've got vector u, let's say, is 3, -4, 8. Vector v is 2, 1, -5. I want you to find theta, the angle between u and v. Okay? So I'm giving you two vectors in 3D. You don't have to draw them. In fact, I don't know how you would draw them. So there's kind of an order of things. So if I look at the formula that we just established, I'm going to need a dot product and I'm going to need magnitudes. Doesn't really matter what order you find them in, but you have to find all three. So perhaps we'll start with the dot product. What is u dot v? So it's 6 plus what? -4 plus -40. So that would be -38. All right? What is the length of u? So that would be 9 plus 16 plus 64 under the root. What's that? Root 89. Okay? What's the length v? That'd be 4 plus 1 plus 25 under the root. So that'd be root 30. All right? I've got everything I need. Don't calculate either one of those. That doesn't even make sense. I'm going to calculate, round it off, and then re-enter it in my calculator, guaranteeing now whatever I report will be wrong in the last decimal place. Not a big fan of that. There's a basic rule of thumb that a lot of folks don't remember. You probably learned as little kids. What do you round off if you're going to report a decimal answer? What part? The last thing is the only thing you round. If you round off along the way, it's an absolute that the last thing you wrote won't be entirely correct. It's called accumulated round-off error. I can absolutely guarantee you, no matter what you said, your last decimal place will always be incorrect if you round it off along the way. No, you got a calculator. Why would you round these off? So what's theta? It's the inverse cosine of -38, root 89, root 30. Now, if I did something goofy, let's say one of the numbers, let's just assume for a moment, let's say one of the numbers is not correct. Boy, it'd be really hard for me to know that I have an incorrect answer. But there's one game changer. What if this was not between -1 and 1?
Error.
Then my calculator is going to say error. Because I'm saying the cosine of a real angle was outside the range of -1 to 1. That's about the only way you really know you messed it up. And you got to really mess it up. Let's just say hypothetically, instead of 30, I put a 3. Or instead of 89, I put a 29. I have a wrong number in there. When my calculator says error, you go, oh, yeah, this is not going to work. So, but if I'm only a little bit off, it's going to work. Okay, it's sort of like, how do you know on a multiple choice test? How do you know when you have the wrong answer? You missed it so badly that your terrible answer isn't even one of the choices. Because the way all multiple choice tests are worked is there's the right answer and then the most common wrong answers. That's why a lot of times you feel really good because you answered, but you made the most common mistake and that was an answer. You got to really mess up that problem, just royally mess it up for your answer not even to be a choice. But now you go, I got it wrong. I did it wrong because it's not a choice. Yes. If you make a small error, it is a choice. So you never find the small errors, you only find the big ones. If you really mess this up, you might be able to discover it. Now, I can give you two different versions of the answer, but I think a degree answer would probably be the more useful of the two. So let's all do that. Make sure you're in degree mode. All right, what do you got?
137.
Yeah, that sounds about right. In the 137 range. Now, It's 137, I don't care how many decimals, let's say 0.34. Now, is that an equal? Well, that's an infinite non-repeating decimal sequence of an irrational number, but I need to report something. And so many of you aren't familiar with the symbol. There is only one symbol mathematically that's ever been correct in this context, and most people don't know it. Equals with a dot. That means approximation. If you're using a calculator and you're rounding it off and reporting an answer, squiggles would be the ultimate wrong answer. Squiggle means asymptotic. The only time in your life you've ever used squiggle was probably when you did Taylor polynomials. Oh, I used the polynomial to do an estimation of the infinite sum and right? Ballpark. Squiggle means it's asymptotic. Squiggle has nothing to do with calculation. But in calculations, the word estimate usually applies to the squiggle. But most people were conditioned as kids to use squiggle as approximation. Why? These hadn't been invented yet. So people didn't know the difference. But the moment you had the ability to do a calculation and then round it off, I'll give you a simple example of, in terms of a numerical value, does anybody know historically what number was often people used for pi because it was real convenient?
3?
Not 3.
22 over 7.
22 sevenths. By the way, if you grab an older algebra book, they'll still say use this because the students literally had no calculators. This is correct. Because 22 sevenths is pretty close. You know, the first couple decimal places agree. I was really bored, and I've shown some of you this. I was proctoring an exam, and I forgot to bring work with me. That is like the worst thing ever. I was proctoring a 2-hour exam, and I didn't have anything to do. All I had was my titanium. So I just started playing around. Do that on your calculator. Try that and tell me what you see. I found an improvement.
That's 2.98.
Did I write the wrong thing? Oh, hold on a minute. Oh, shoot. Give me a second. Sorry. Can't remember my own thing. Hold on. I'm sorry, 113. 113, sorry. God, I've even forgot it. You got to go back and do it again. Sorry, 355 over 113. What do you see as a decimal? A lot more decimals. Now, does that equal pi? No. But it's so close, could it be used as a replacement for pi if the calculations aren't astronomical? Yes, that's why estimators are really, really useful. That's why people used this. But if I was talking something really, really large, now we get a little bit away from it. This is a class where we are only going to do one problem in this course where we do estimations, and that's the tangent plane estimations. In Calc 1, do you remember you had the tangent line left the curve, and you used the value on the tangent line for the value on the curve? That's not an equal, that's not an approximation, that's an estimation, that's a squiggle. Why? Because squiggles become equals based on limits. Oh, calculations never become equals because I can't write all the decimals. But asymptotic means if I take a limit in one direction, they will eventually be equal again. That's the major, major difference. Again, think Taylor series, Taylor polynomials. Right? You had the first few terms of your Taylor series was a great estimator. More terms, better. Those of you who were in my Calc 2, right, we did a lot of stuff with Desmos. It was unbelievable, the power. With a few terms, we could have 10, 20 decimal place accuracy. It wasn't equal. But for all practical purposes, it was just as good, and then I didn't need any powerful technology. So this probably, again, good form, degree. I'm not nitpicky, but it will happen, certainly on an exam, you had every good intention and you left your calculator in radian mode. And you gave a radian answer, meaning to do a degree answer. If I don't put units, what is the default? It's actually radians. It actually isn't degrees. That's why it's good form, right? It's good form. If there's no possibility that anybody's going to be confused, but I could say a radian answer. When you did things like rotation of axes in Calc 2, so what's the angle of rotation? Sometimes you said pi over 6, sometimes you said 30 degrees. Both were correct. But you didn't ever say 30. You said 30 degrees because you could have also said pi over 6. Did you have to say the word radian? Technically, no, although a lot of people do because they want to be certain. The default of an angle is always radians. So it's good form. Now, That's dot product. There's really nothing about it that's terribly tricky, but there is one major application of dot product. Those who've had linear algebra know this one. It's probably the most important application in use of dot product, and it's something called projection. Strangely enough, a lot of the calculus books don't have this. They'll do the dot product, but they don't show you the projection. The projection is the most important use of dot product. See, when I said I want to push that refrigerator across the room and I pushed it this way, how much of that was in this direction? I need that vector. That's called the projection. The projection of that vector into this, I need an actual vector there. So you get the picture. I'm going to do it in 2 dimensions. The results apply in all dimensions. I just can't draw things in 3. So let's take a vector. We'll call this vector v. Let's take another vector. We'll call this vector u. I don't want them to be at right angles. Now, this might be, I want to go and apply force, but this is the direction I actually went. What I would like to know is, make that a right angle. I want that vector. You see, when I push in this direction, and you go to where I pushed, now you want to go across to where I want to go. Aren't there an infinite number of line segments? Which one do you choose? You got to choose the one that's perpendicular because that's the shortest. It's always the perpendicular. See, there's an infinite number of line segments I could draw, but this is the only one that represents how much of this is in this direction, because I could also have, a different direction. I want this vector right here. This vector is called, I'll write it up here, it's called the projection of u onto v. Could I have done v onto u? Could I have gone the other way? Sure, it'd be a different vector, and I would swap the roles. This is the guy that says what direction it's going. Now, the orange vector here, do you agree that it's simply going to be a scalar multiple of v? Does that seem reasonable? It's going to be nothing more than a scalar multiple of v. So I need to do 2 things. I need to figure out how long it is, and then once I figure out how long it is, then all I need to do is multiply that by the unit vector in the direction of v. Everybody cool with that? There's a little guy here. That's the unit vector in the direction of v. I need this length multiplied by that vector, and that will give me the projection. Okay? So I'll write it this way. Whatever the magnitude of the projection times 1 over the magnitude of v times vector v. Scalar, scalar, v. Well, how do I find the magnitude of the projection? Well, I know v and I know u. Those are given. Okay? They're given. So I can find their magnitudes. I can find the length of u, I can find the length of v, because I gave you u and v. That's not ambiguous. I didn't give you theta, though. But do you agree there's a SOHCAHTOA here? So exactly how long is the projection? I need this magnitude. I don't need the vector yet. I need this magnitude. How long is this? SOHCAHTOA. Well, that would be the hypotenuse. So if the cosine of theta should be this over this. So what is the projection? Shouldn't it be magnitude of u times the cosine of theta? Yes, no, maybe? Yes. The magnitude of u, that's, again, think hypotenuse. So the cosine of this is that length divided by that length. That's, okay? So that means my final answer, the projection of u onto v is simply going to be this, length u, cos theta, times 1 over length v, so I'll just put right here, times vector v. Great, I know this, I know this, I know this. I guess I could figure this out, but that's a little messy. You know what would be really helpful? Let me put a little space here. Push. You know what would be really, really helpful? If there was a length v there. Do you agree? If there was a length v right here, that would be really useful, wouldn't it? But there isn't. Oh my God, everyone look. Everyone turn around. It's Elvis, I'm pretty sure. Oh, sorry, it was Professor Mona. I was getting confused. Oh, look at that. I have a length v. Can I do that?
Multiply by 1.
The ball.
What's my numerator now?
Dot product.
Very specifically,
U dot V.
u dot v. What's my denominator?
V dot V.
It's v dot v. And that is one of the simpler formulas to apply. We never had to find theta, did we? Everybody see that? That's a huge bonus. This is a scalar times vector v. We said our answer should be a scalar multiple of vector v. This is what it is. So those who've had linear algebra, hopefully you're very familiar with that, because then this is the thing we use in the Gram-Schmidt process over and over and over again. It becomes huge. But the nice thing is, let's assume that most of the time when we're working with vectors, not making unit vectors, just I'm giving you vectors, most of the time our components are just integers. I mean, they're usually not complicated things. Finding a magnitude is going to involve a square root. But the vector that you're usually working with is probably happy numbers. So that means, in all likelihood, this is a rational number. Right? It's not going to be something nasty. It's going to be something pretty simple. And then times this. Does that make sense? What if I wanted to do the projection of v onto u? Well, then the u's and v's need to kind of swap places. You notice that v kind of wins, doesn't it? Yeah, the one that I'm projecting onto is the one that shows up a lot. That's really important that we recognize that. That's a formula, okay? And it is, again, probably the most practical formula, because if I'm actually performing a dot product, then literally this is the vector I'm dotting my original answer with, okay? Any question on this? All right, we're done with dot product. Now we're going to get into the messier one. The cross product. I don't need you to have any working knowledge of a cross product. And in fact, sometimes it's easier not to have worked with them and start from scratch, because then you don't have any preconceived notions of what to do, what not to do. So the idea of cross product is I want to invent something that when I apply it to two vectors, my result is another vector. Now, the great limiting part of cross product is that cross product is only defined in R3. Dot product is defined in all dimensions. Cross product only lives in R3. Okay? So that's a huge limiting thing, but cross product shows up all the time. So here's the idea of cross product. And by the way, I guarantee you've never seen this, because I never saw this. It's not in any book I've ever seen. It's not on any YouTube video. You're not going to find it anywhere. And that is where it actually came from. Everybody tells you how to do cross product. And you say, okay, I'll do this, but what was the point? Why is this important? Where did it come from? There's a formula. Who came up with the formula? A number of years ago, I was teaching a Calc 3 class. It wasn't even linear. And someone said, where does it come from? Because everybody makes us memorize it, and they were saying they'd been asking their physics professors, and I'm like, I don't know, it is. It just is, so don't ask about it, just do it. And I'm the person who always said why. When I was in the class, I was never happy unless I got the explanation. And a lot of questions that I had were not answered. So I sometimes figured it out on my own. Sometimes it was a little over my head, but I figured it out on my own, because I don't like no, do this because I said so. Does anyone here have children? Okay, I have many. I have enough for all of you. The because I said so stops working around, I don't know, 2, maybe 3 years old. So when your kids say why, you kind of have to have a reason now. Don't play in the street. Why? Because you're going to get run over. Okay, you don't say because I said so. You actually have to give a reason, and you can have a conversation. And now, now my kids are all grown up, and they tell me to do stuff and I say what. So cross product, the idea is this. Consider vector U, U1, U2, U3, vector V, V1, V2, V3, and vector W we're going to define as U cross V, and we actually use an X in this context. That's the symbol we use. The dot product, we literally use a dot. I'm going to have a new vector, we'll call it W. And the entire point of W, okay, and this is the part that's huge. All right, I like it when I had yardsticks. Well, there's one of them. Is there any other ones? I'm not going to do the graphing process, don't worry, Ian. You remember when I did that? I always have vector people. Sometimes I'll use your arms. Okay. I need something, I'll use my own arm. All right, here's a vector. Now remember, all vectors are oriented from the origin when you're describing them in component form. So I have a vector coming out of the origin, and let's say my arm's another vector coming out of the origin. These vectors will uniquely determine a plane. Now, don't take two vectors that are multiples of each other. They live on the same line. There's infinitely many planes that pass through them. So I need two vectors that are not multiples to start with. Does everybody understand? If I take two vectors that are multiple, let's take the line running along the floor. How many planes can pass through that line? Infinitely many. Now I have my two arms, if you will. How many big pieces of cardboard could you lay across my arms? Just one. They uniquely determine a plane. So the plane that I'm uniquely determining, what I want is for W to be orthogonal to that plane. So here are my two vectors. I want to create this vector here. Regardless of where those two vectors are pointing, and we're going to do this with three-dimensional motion soon enough, regardless of where these two are pointing, I want a vector that is orthogonal to these vectors. And something about the length I want to be preserved. Okay? In fact, if these vectors are at right angles, I want the length of this one to be actually simply the product of these two lengths. So I need to create something. And here's what I'm going to create. I need u dot w to equal 0, and at the same time, v dot w. I want to invent a vector w so that both of those statements are simultaneously true. And then what does that mean? That means w is orthogonal to u, it's orthogonal to v, therefore it must be orthogonal to the plane that u and v live on. Because if I'm orthogonal to u and v, then I'm orthogonal to every linear combination. So in case you don't get this, I'll put them up so you can see them. Here's two vectors. If I say, okay, take 3 of these and 5 of these, now I have a new vector. Take -2 of these and -6 of those, now I have a new vector. Every linear combination of these two vectors, any two scalars you want to put, I will eventually fill in the plane they live on. Every vector on this plane ultimately will be a linear combination of these two guys. Not just multiples, but multiples added to multiples. Everybody with me on that? So I need to create a vector that's orthogonal to every linear combination of these guys. Yikes. This is good enough. So to do this, that means I'm going to have a system of equations. So I need, and let's call W, sorry. Let's call W. How about W1, W2, W3? Let's call it that. So I need U1, W1 plus U2, W2 plus U3, W3 to equal 0. I need V1, W1 plus V2, W2 plus V3, W3 to equal 0. Now, I don't want to use matrix algebra here. For those of you who know matrix algebra, the simplest way to solve a system when you have more than two variables is with the matrix. But that's not what we're doing, so we can still use the addition method, right? Remember, you take a multiple of one equation, add it to the other, eliminate a variable. So let's do that, and let's start by, how about, let's eliminate W3. So for me to eliminate W3, I don't, W1, W2, and W3 think of as your variables. You don't know what they are, but you know what the U's and V's are. Those are constants. So let's multiply this equation by V3 and this one by U3, although I need to make one of them negative. Okay, so let's say we multiply this one by V3. So you like that? Right side by V3 is nice. And then let's do this one by, how about negative U3. And what will I get when I do that? I will get U1V3 W1 plus U2V3 W2 plus U3V3 W3 still equals 0. Here I'll get negative U3V1 W1, negative U3V2 W2, negative U3V3 W3. Okay. Now I can add these together. Those are gone. And what will I now get? I will now get, I'm going to add the coefficients up. Okay? So I'm going to get U1V3 minus U3V1 W1 plus U2V3 minus U3V2 W2 equals 0. Okay? Oh my gosh. Well, the nice thing is, I'll keep it really simple. If I said 2x plus 4y equals 0, could I choose x to be negative 4 and y to be positive 2? Or choose x to be, in other words, if I just pick the other coefficient, would that work? But I have to change the signs, don't I? So there are an infinite number of solutions, but the first solution we would get, for those who've learned how to parameterize, it'd be choosing your parameter to be 1. Could I simply say then that W1 is going to equal U2V3 minus U3V2, and W2 will just be the negative of this guy, which will be U3V1 minus U1V3. And now that will work. To save time, I need to do this entire process again, but now I'll eliminate one of the other two variables. You with me on that? So I would choose a different one, and I would do the exact same process again. I'll just speed it up. When I do the exact same process again, my W3 is going to be U1V2 minus U2V1. If I do the exact same process, and I add them up, I'm going to get the exact same thing. We have just figured out a solution to that problem, and we're going to check it, by the way. We're going to check it by doing a dot product. So it appears, I'll write it here, that my W is going to be, where's W? And there it is. U2V3 minus U3V2. W2 is U3V1 minus U1V3. And then W3 is U1V2 minus U2V1. I left the U's, V's in alphabetical order to keep track of. Now, I'm pretty sure that this will work. What was the goal? To create a vector that was orthogonal to the plane that the other two vectors lived on, which means to check, all I have to do is see, is W actually orthogonal to U, and is W simultaneously orthogonal to V? How do you do that? Dot product. And this is the simplest check there is, but it's the check a lot of people fail to do. Let me erase this. We have all that up there. All right, so let's do U dot W. I'll just check one. Okay, U dot W. So it's U1 times all of this mess. Yikes. All right. Now understand in general, this is going to be one value, isn't it? It's just going to be a number. You're not going to have a bunch of stuff going on there. Plus U2 times U3V1 minus U1V3. Plus U3 times U1V2 minus U2V1. This will strain the die on me. All right. Well, this is U1 U2V3 minus U1 U3V2 plus U2 U3V1 minus U1 U2V3 plus U1 U3V2 minus U2 U3V1. Boy, what a mess. Oh, except that, you know what? These guys cancel. Oh, okay, good. Oh, and these guys cancel. Oh, and these guys cancel. Is that a good thing? Yeah. Do I need to do the other one? No, it's going to work. We've just come up with a vector that is simultaneously orthogonal to the first two. That's what the cross product is. But don't memorize that. Too messy, too difficult. There's a simple way. And most people learn the most horrific, long, awful way. You learn, I learned to do it using a determinant, which is great if you know linear algebra. In a class like this, cross product is supposed to be considered a remedial arithmetic level. And I'm going to tell you right now that at 50% of all cross product answers produced in this class for the rest of the way, 50% of all the answers are going to be incorrect. Because people hang on to a method that doesn't make any sense and they don't understand because they don't know linear algebra. In other words, unless you work with determinants all the time, most of you don't know how to take a determinant. And you put a vector in a determinant, which mathematically is like scratching a chalkboard with metal claws. Determinants can only take scalars or scalar valued functions. A vector can't be in a determinant, can't be in a matrix. That's impossible mathematics. But that's what they showed me, and it made it so much easier. No, it didn't. It made it really long and difficult. I'm going to show you the right way, the easy way. Multiply, subtract, multiply, subtract, multiply, subtract. When I do a cross product, I don't think it takes me 10 seconds, ever. Literally, I can't imagine a cross product taking more than 10 seconds. When students do it, it takes them 10 minutes, and they get the wrong answer most of the time, because they don't understand when you do a determinant, there's certain rules apply. And I say it laughingly because I've been teaching this for a million years, and people hang on to really archaic methods that aren't very good. All right, 6, -1, 3. B is 2, 4, -5. The only thing I suggest when you're doing a cross product, stack your vectors. Stack them. Put one on top of the other. Now, follow along with me. 5 minus 12. 6 minus -30. 24 minus -2. That's it. You didn't learn it that way, you should have learned it that way. Most of you would be doing a really complicated process, and I'll give you a hint. Most of the time, your middle number is going to be incorrect. Most of the time. How do I know? Because I've taught 10,000 students Calc 3. And most of the time, it's not the first and last, it's their middle number's wrong. But there's an absolute simple way to know that you're correct. Take this and do the dot product with either one of these. Doesn't matter. It cannot be orthogonal to one and not be orthogonal to the other. That's impossible. If you have a right answer, it's orthogonal to both. If you have a wrong answer, it's orthogonal to neither. So you only have to check it once. But this is a check that you must do every single time because the process is not complicated, but I don't want you walking away saying, I hope I did the cross product correctly. Oh, no. Okay, let's do a quick check. Let me do U dotted with my U cross V. Real quick check. Here's the nice thing. I'm either going to get a 0 or I'm not. So 6 times -7, -1 times 36, 3 times 26, and I'm pretty sure that's it. Right, rejoicing, confetti everywhere, just, celebrations. No, I didn't mess it up. That's all that means. The concept of cross product was to create a vector that was simultaneously orthogonal to the original two, meaning it's orthogonal to the plane you live on. Because the next thing we do next day is to talk about how do I write equations of planes? How do I do all of this kind of stuff? And it's very powerful stuff, okay? But that's it. So that's the answer. There's not much to do with it. Yes?
Will you run through it one more time?
Yeah. I had a student a number of years ago, he had really flexible, and he would do it with his fingers, and I tried it, I think I pulled a muscle. But you're starting here, so you take that product minus that product. Now you're going to go to the outer ones. So move your finger to the left, that product minus that product. Now you're going to do the first two, so that product minus that product. How do you do it? do with his fingers, he could make them like slide on his hand, and it was kind of creepy. But again, boom, 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 boom. You have to do it a few times, and if you do it 2 or 3 times, you gotta go, I got it. And the nice thing is, you say, well, what if my numbers are huge? Well, then you pull out one of these, but it's still the same process. But always do the check. Why? No matter how simple this is, could I have multiplied or added badly? If I gave you 100 problems and asked you to do it, if you knew this inside and out, you're still only going to get 95 of them right, because we're all going to make arithmetic mistakes occasionally. All of us will occasionally make an arithmetic error. That's why you got to check it with the dot product, and the check is way faster than the original. Question?
Correct me if I'm wrong, but like instead of memorizing like the outer and inside and stuff like that, would it be right to say like because you stack them?
Well, this is the formula, but that's too much to remember, I think.
No, I was talking about the stacked one right there when you were doing like this and this like that. So like if you want the first one, which is number -7 right there, you would like I guess leave out the 6 and 2 right
Well,
there.
yeah, back up one. It's exactly what's going on. You notice there's no subscript of 1 in this term, there's no subscript of 2 in this term, there's no subscript of 3. So that's half the battle is realizing, oh, in the first position I'm not using to get the first position I'm not using either of the first 2 numbers, I'm using everything else.
Okay.
That's why you're usually going to start, you're going to go in this order. So I'm starting here, so that means I'm going to use those 2 guys. Then for the next one, I'm going to use the outer ones, and then for the next one, for exactly what you just said.
Yeah.
Again, in the finished formula, look at the subscripts. Right, the first position doesn't use U1 or V1. The second position doesn't use U1 and V2 and so on. So, okay, well, I'm just going to multiply and subtract, but I got to do it in the right order. If you know what you're doing, you're going to be right the vast majority of the time, and you're going to check it by dot product really quickly because the check is so fast. But if you don't check it, then you're not going to have absolute certainty. Now, there are some very, very powerful properties now of cross product. One of them is magnitude, okay? And one of them is the relationship between your results and your original guys. So this is the part where I will fill up the board. Because now that I have vectors in R3 and I need magnitudes, I'm going to have sums of squares 3 long, and I'm going to have, yeah, are you excited to find the magnitude of that guy? Yeah. No, but I need it to answer questions. So I'm going to bring up what I have on Canvas right now, so I can walk you through. I don't need you to take notes on this. I've already done it. All right, Samuel, I might need you. Apparently you have the touch. Oh! Now, correct me if I'm wrong, didn't this used to go below the chalk tray? Does anybody ever use these in your other classrooms? Never? Okay. No one ever uses the computers? You have these wonderful computers, you probably should use them.
Yeah. And physics, like last semester.
Isn't that a little high?
Yeah, no, last semester, like you're saying, it was well below.
That's what I thought.
It was also a different classroom, but I don't know
Well,
how consistent. I don't know how consistent they are.
Better and the screen is like really good.
Well, as long as we can fit everything on it, we're good.
I mean, they're aligned. correctly.
Some of these results you may actually know because you've done this before. It's not just knowing the results, it's knowing the why. You're math people, you need to know the why. You don't just want to know the answer, you want to know why the heck is that the answer? You know, why that and not something else? And that is the question of the day. Okay. I apologize for the slowness of all this, but you'll appreciate this later because I'm not going to have to do all this again. All righty. Okay. All right, I'm going to turn off the light here a little bit. Yes, yeah, about right now you're seeing the Matrix movie, right? Everybody know? You know what I'm talking about? Yeah, all the ciphers running down the screen. There's like millions of pieces of information. So right now, I said make the following observations. Okay, based on what we now know the cross product is, I want to square the magnitude, which is going to be the sum of all those squares. Yikes. Here's what I want to do. I want to calculate that, and I got this. Okay, big, long, and icky. I also want to take the magnitude of u squared, which is that, times the magnitude of e squared, and then multiply that big, ugly mess out. And then the third piece of the puzzle, I want to take u dot v, which is real easy, and then I want to square it. So I'm squaring trinomials all over the place. A lot of stuff. None of it hard. All of it is actually pretty easy, but the fact that it's in the u1, v1 form makes everything really long because you don't have one number. So I have this quantity here, I have this quantity here, I have this quantity here. Now, if you stare at them, and some of you are a little far away, again, if you go to Canvas, it'll look a lot bigger. But if you notice, in these three terms, you see all the exact same terms. In fact, very specifically, normally this takes me all three boards and I fill them up and people's eyes start going in every direction at that point. But if you notice that if I take this quantity here and I subtract this quantity here, and you can just look at, oh, okay, then those guys are gone, and then those two are gone, and then those guys are gone, and then all of these guys will have negatives, I will get exactly that quantity there. That's what I want you to notice, that when you look at all this horrific algebra, that if I take, again, this quantity here and I subtract this quantity here, I will get exactly this quantity here. Why is that important? Because that's the first major result. You guys all write it big. So the first major result is that u cross v quantity squared is in fact equal to this. But that's a lot of work. I got to do a lot of work to find the magnitude of that squared. Can I just square it? Yeah, but what I really want to do is get an angle in there, like a sine angle or a cosine. Remember, you're going to go outside at some point. Oh, in other words, I'm not going to have vectors of components. I'm going to have, all right, I have this vector and that one, and I have that one, and now I want you to do the cross product. So, look at that guy. What is u dot v in terms of magnitudes? Isn't this length u, length v, cos theta? Oh, so I'm going to apply the square. Let me just go and apply the square to each one. Square, square, square. I can factor this out. And now what do I got? I've got length u squared, length v squared, 1 minus cos squared. 1 minus cos squared. That's vaguely familiar, isn't it? It's sine squared. And in the first and second quadrants, sine is never negative. So I can take the square root of both sides, and what do we get as a result? That the magnitude of u cross v is equal to length u, length v, sine theta. Well, that's convenient. What was the magnitude of, what's the dot product? Length u, length v, cos theta. The magnitude of cross product is length u, length v, sine theta. And since sine theta is never negative, that doesn't present a problem. But can that quantity be 0? What would theta have to be for that to be 0?
0.
0. That would mean my two vectors are in the same direction. Now think about this for a moment. Didn't we say earlier that the 0 vector is orthogonal to all vectors automatically? Because dotted with all vectors, it's going to give you 0. So I've got a vector running along the floor, and then I have a second vector, or you should say on the corner here, and then I have a second vector that's just a multiple of that vector. Is there exactly one plane these live on? No, there's infinitely many planes. Oh, yikes. And their cross product needed to be a vector that was orthogonal to the plane they were formed. But there's infinitely many planes, so the only vector that it could be would be the 0 vector. That's the only vector that would automatically be orthogonal to every plane, wouldn't it? So if two vectors are pointing in the same or opposite direction means they're still scalar multiples. Two vectors are pointing in the same or opposite direction, they live on the same line, then their cross product will be the 0 vector. That's actually proving it right there, but that also makes sense geometrically like I just explained. Okay? Can I use cross product to find the angle between two vectors? By just working backwards and doing inverse sine. Can I do that? Is that legal?
Yes.
Will I get the right answer 100% of the time? How often will I get the right answer? Exactly 50% of the time. Why? I will only get the right answer when theta is acute. Oh, because if theta is obtuse, I'll always get the acute answer. Does everybody understand that? Inverse sine doesn't return the second quadrangle. So that's why you don't want to use law of sines in general, or I'm sorry, you don't want to use, the sine in general to find the angle. You want to use the cosine, because then you get your obtuse angles if that was the correct thing. Now, here's the other thing. If my vectors are at 90 degrees, I said that should maximize. Remember, if they're in the same direction, my cross product is the zero vector. I'd say that's minimizing it. They're 90 degrees. My cross product is a vector that is orthogonal to both of these at the same time, and its length will be length u times length v, times the sine of 90 degrees, which is 1. So the maximum length of a cross product are when my original vectors are orthogonal. By the way, that's also the minimum of the dot product, isn't it? So they kind of work opposite directions there. That's kind of a powerful notion. Okay, everybody cool with that? So this is on canvas for you to look at, and if you need anything to help you fall asleep at night or something, look at that. Okay, I'm going to do more stuff, but that's the part I didn't want to write down, just because it's narrative. Yeah.
Does the magnitude of u cross v squared on the whiteboard? You wrote it on the whiteboard.
Right.
That one.
So squared, everything's being squared. So therefore, if I remove the square, it's just length u, length v, sine theta.
But that doesn't, the cross doesn't mean multiplied?
Well, cross product is this thing we've just defined.
Okay, yeah. I just want to make sure that that x does not mean
Well, no, we've defined two forms of vector multiplication. Dot product is one of them, when we just use the dot, and cross product is the other, we use the x. There's never going to be anything else that looks like that. So that's a good question. There's no ambiguity created by that. Because if I said multiply these two vectors, you would be asking me, dot product or cross product? It does matter, doesn't it? You can't just multiply vectors. There's no defined vector multiplication, but we've defined dot product. We've now defined cross product, because now they have physical uses for us. So, first question. Is cross product commutative? Dot product was commutative because the dot product was the sum of a bunch of products. And multiplication and addition are both commutative. But what's cross product? The difference of a bunch of products. And subtraction is not commutative. If I do v cross u, I will get a vector in the opposite direction. I'll get -1 times u cross v. Cross product is not commutative, and it's really important that we recognize that. That does change things knowing that. Now I'm going to go ahead and turn this off. So I've got my two vectors, and I keep using the same. I used to do this with my fingers, and they always cramp up, so I try to use the vectors. So I'm going to do the cross product between these two guys, and we keep saying it's going to be this guy. Couldn't it also be this guy? Oh. They're on the same line. How do I know which one it is? Okay, let's keep it really, really simple. I have a unit vector along the x-axis. I'm crossing it with a unit vector along the y-axis. Where should my answer be? It should be along the z-axis. Do you agree with that? That should make perfect sense, because the z-axis is where I'm just doing the xy plane. And I'm doing unit vectors to make it even easier. So what is this going to be? Well, let me put this below it. I don't like even having to think. So it's 0, 0, 1. Okay. So it's that guy. But what if? What if I had reversed the order of the cross product? Then what would it have been? It would have been the negative of this, which would have meant point the other direction. So how do I know? Well, let's see. If I take my first vector, which was going that way, and my second vector was going that way, well, my answer should be going that way. But if my first vector was going that way, and my second... It's very important. absolute law that took years and years and years, and the proof is probably like 1,000 pages long. What's it called?
Right hand.
The right-hand rule. Yeah, it's pretty trivial. Does it matter what order you do the cross product? Yeah. The right-hand rule, unless you have unbelievably flexible fingers, think of it logically. Point your fingers in the direction of the first vector and close your hand in the direction of the second vector, and your thumb will point in the direction. Mainly because I gave you such a simple example, you all agreed that my answer should be on the z-axis. But is it that way, or is it that way? It depends which way I'm crossing them. Oh, so this guy crossed that guy, gave me that answer. That guy crossed that guy, gave me that answer. Does that matter in reality? Yes. Has anybody here ever had to change their own tire? The most terrifying thing, I know all of it, especially jacking it up, on your curb with your crappy jack that your car came with, and hopefully you don't have to put your head under there. And you get your lug wrench and you start turning it, and you're using all your strength, because those guys at the tire place, they used power tools to tighten the lug nuts, didn't they? So you're working on this thing for a few minutes, and then everybody who's ever done this has the same horrific thought. Oh my God, am I just tightening them? Have you guys ever had that thought? Everybody has that thought. It's not going anywhere. I may be making the situation worse. I may be tightening them. You should know which way to go. There's one of those laws of physics that everybody learned as kids. What is it called? Righty, tighty, lefty, loosey. That's actually the cross product. Believe it or not. It is. My tire is here. To tighten it, I have to turn it clockwise. Because when I do it clockwise, which way is my force going? To unscrew it, I have to turn it counter. The righty-tighty, lefty-loosey is a little vague because it's only right at the top of the turn. It's left at the bottom. So it probably should be more like clockwise, tighty, counterclockwise, loosey. But that just doesn't have the same feel, does it? But that's actually a more accurate depiction. So you're screwing on the lug nuts or taking the lug nuts off. You've got to go counterclockwise, because going clockwise is tightening it. How do you know? Because the force is aimed this way. Okay, everybody with me so far? So anytime you're unscrewing something, that's pretty much how it works. Unless
They use left-handed screws.
no, it's called a child safety cap. What it means is they made it human-proof. Because you're sitting there and you can't unscrew the darn thing because you're trying to do the righty-tighty, lefty-loosey, and it's reverse-threaded. And when you tighten something, you tend to lean on it, don't you? Push down. When you untighten something, you tend to want to pull it away. But the reverse one, you've got to push on it in order to loosen it. It's made so that it defies the usual conventional wisdom to make it harder to open. That's supposed to protect the kids. Although I find adults have just as much trouble. So, but righty-tighty, lefty-loosey is essentially this, because you are applying a vector force, and think of the result then. The direction of, you now know the result. So that's kind of a cool little example, isn't it? That the vectors apply to something every day of opening up something or tightening something, okay? So if I gave you any two vectors in R3, at this point, you could tell me their magnitudes, you could tell me the unit vectors, you could tell me their dot product, you could tell me a projection of one onto the other. You could tell me the angle between them, you could tell me the cross product, you could tell me the magnitudes. All of these things you can do now. Okay? Is everybody okay with that? It's like, wow, that's a lot of stuff. On Canvas, if you look, there's something that says vector worksheet. That's what that is. That's one of those things that everybody needs to be able to do every one of those problems. It's a really quick summary of just what we've learned. Dot product, cross product, projections, little things. But also making sure that sometimes the answer is a scalar, sometimes the answer is a vector. And it's very important you know which one's which. A projection, a cross product, a unit vector. Those are vectors, obviously. Dot product, angle between, magnitudes. Those are all scalars. Sometimes we get them reversed inadvertently and it messes us up. So now I want to talk about the plane. Okay. If I give you two distinct points, we know there's exactly one line that passes through them. If I give you three distinct points that are not on the same line, the term is non-collinear. If I give you 3 points in space, and there's no longer one line, is it? But there's only one plane. If I give you 3 points that are not on the same line, now if I give you 3 points on the same line, there's infinitely many planes, aren't there? But if I just gave you 3 random points that were not on the same line, there's exactly one plane that passes through them. So, you know, only one plane. It's not about lines anymore, it's about. So what if I give you 3 distinct points? I would like to know a vector that is orthogonal to the plane that the 3 points live on. Now, if I'm starting with 3 points, there's not even a plane, but there's definitely going to be a unique direction. So imagine I gave you 3 points on the floor. Then obviously this would be the direction. It's automatically oriented at the origin because I'm doing it in component form, okay? But it could be pointing this way, it could be pointing that way, and both would be correct. This is called a normal vector, okay? It's an odd choice of a word because we have 2 types of vectors. Everybody knows that, right? Normal and abnormal. No, sorry, I had to throw that in there. The normal vector just means you're orthogonal to whatever you're working with, whether it's a surface or whether it's a plane. But a normal vector is orthogonal. Again, I'm not sure why we chose that word, but all throughout this course, whenever we refer to something being normal, it always means it's orthogonal. So I'm going to give you 3 points in space, and I want you to come up with a normal vector to the plane they live on. Boy, that sounds like a tall task. Well, so here's what we're going to do. I'm going to do this in 2 dimensions first, okay? I have a point here, let's call it x1, y1. And then I have another point over here, let's call it x2, y2. I have a line segment that I can easily draw between those 2. That's a line segment. I would like to create a vector. Now the vector automatically is oriented at the origin because that's how we always describe things as oriented at the origin. So essentially I want that vector. So what will this vector look like? Well, it turns out it's going to be x2 minus x1, y2 minus y1. Because think about this way. Think a little right triangle. The change in x would be x2 minus x1, and the change of y would be y2 minus y1, and oh, this would be the same right triangle if I drew it here. So if you're given 2 points, you can create a vector. A lot of people say, well, I just subtract points. No, you can't subtract points. Points have no numerical value. You take the vector of the differences in the coordinates. You don't say this point minus this point. That doesn't make sense. You say the vector of the differences of the components. That's how you create a vector anytime. So I'm going to give you 3 points in space. I'll just be generic. P, let's say, is -2, 1, 0. Q is 3, 4, 2. And R is -3, 2, -1. All right. These are 3 non-collinear points. I would like to create 2 vectors and then simply take the cross product of those 2 vectors, and that will be my answer. So do I have a lot of choices here? Actually, I do. So the first thing I need to do is decide which one is going to be the vertex. Oh, I do not want to say, okay, here's one vector and then here's another vector. No, 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 no. If that's one vector, I need 2 vectors to share a vertex. So probably the easiest thing is create a vector PQ and create a vector PR. This is kind of the most universal way. And we simply will call it PQ. So if I go back to this picture, if this was point P and this was point Q, then this would actually be PQ. Okay? And part of the reason we do this is I have a point here, I have a point here. I can create a vector, but that vector can't live here. There's no way to describe it. This starting point, I still have to move over to the origin. Okay? But when I go outside, yes, then it's fine. So what is PQ? So you're going to, this minus this. So it's going to be 5, 3, 2. Yes? No? Maybe? Hopefully? PR, so -3 minus -2, 2 minus 1, -1 minus 0. So far, so good. Was that difficult? No, there's no way I could make that difficult. That's pretty simple. That's gonna be simple every time. Now, we usually just call it little n. N is going to be the cross product of these two. Okay, now remember, my first component doesn't involve the first component. That's how I know where to start. So -3 minus 2, -2 minus -5, 5 minus -3. Okay? I think I did it correctly. Let's do a quick check. 5 plus 3 minus 8 is 0. Okay, good. That's how simple and fast the check should be. I have just found a vector that is orthogonal to the plane that these 3 points live on. Is the answer unique? I did things in a very specific order. Did you have to do them in the same order that I just did? Could you have said QP and QR? Could you have said RP and RQ? Could you have done the cross product in reverse order? Oh, so do you see there are multiple setups for this problem? So how many different final answers could I conceivably get in this problem? You want to guess? Okay, are you counting? You're thinking two. I get this one or the negative of this one, no matter what I did. If you chose a different vertex, you would have gotten completely different vectors, but your cross product would have still been the same. Isn't that crazy? How do I know that? Because I did it in my head really fast right before I... No, that's not it at all. I think you want to see that one. That's just kind of cool. All right. AB algebra. Well, actually, AB geometry. That's supposed to be a parallelogram. Okay, it's a parallelogram. All right? Do you remember the area of a parallelogram? It's actually simpler. It's the same as the area of a rectangle, base times height. So I know the area of this parallelogram is base times height. Okay? Do you agree? So it's A times H, except that, well, nobody told me what H was. I have A, B, and I have theta. So is there a SO-CA-TOA relationship here? What is it? Is it SO, Ka, or Toa? It's a SO, right? So what is it? The sine of theta is height over b, so height is b sine theta. In case you didn't know, that's actually a formula for the area of a parallelogram if I don't know the height, but I do know the angle. Okay, so that's really interesting. I feel like I've seen this before. Isn't this the magnitude of the cross product? I have two vectors in R3. I have to be in 3D to discuss this problem. I have two vectors in 3D. I can lay them both on the board. That's not a problem. I can put them both on the floor. I have two vectors in 3D. I know the magnitude of the cross product is this length times the sine of that angle, but so is the area of that parallelogram. Do two vectors in space, I don't know if I have enough fingers for this. Do two vectors in space uniquely determine a parallelogram? Okay. The answer is yes. Just finish it. Two vectors in space clearly uniquely determine a parallelogram. And the area of that parallelogram is equal to the magnitude of the cross product. That's pretty cool, isn't it? By the way, what if I only wanted the area of the triangle that they uniquely determined? You can just take half of that. That's a common question. Whoa. So the area, so that's why I said, now going back to this, it would not have mattered which two vectors I created, because these two, think of it this way. Where's my, sorry. One of the nice things about cross product, and a lot of things we're doing, they tend to be very forgiving because a lot of times the order really won't matter. I'm giving you 3 points in space. And you decided to make two vectors out of it. But instead of making two vectors out of this, what if I make a parallelogram out of this? Okay, it's supposed to be a parallelogram. I should stick with circles and spheres, I know. Do you all agree that this only has one possible value for its area? But it wouldn't matter whether I said these two vectors or these two vectors, or it wouldn't matter which two vectors I took as the cross product. Remember, you said there was multiple ways I could have started this problem. But no matter what, you still would have gotten the same parallelogram, wouldn't you? And the area of the parallelogram is the magnitude of the cross product, which means that the only difference I could have gotten was a negative times this, because it still would have been the same magnitude. That's why I said it wouldn't have mattered. You were going to get the same answer or the negative of that answer no matter what you did. And that's a good thing, because all I was interested in was a direction. Whether it's pointing up or pointing down was not important. I needed it to be orthogonal to the plane that they lived on. Okay, so that guarantees it. That's kind of a cool one. Now there's one other one that's really kind of cool. All right, let me go back to my picture. Well, just generically, you know. I would like to know how far is this point from the line passing through these 2 points? Or how far is this point from the line passing through these 2 points? Or how far is this point from the line passing through these two? Do you agree that all of those are different answers? How the heck would I do that? I asked this question, I think it's on your quiz too. And I'll have people say, well, I went to the internet and I found this, and they prove things over the next course of 10 pages, and I'm usually quite confused at that point, ready to retire. And I have no idea what they did, and I never have had anything remotely correct. Like, why are you making it so complicated? Use what we just did. I need you to find that distance. How the heck am I going to do that? I know that point, I know that point, I know that point, so I know that magnitude, I know that magnitude. I know all the numbers. I don't know the height. If the area is base times height, and I'm asking you for height, wouldn't it just be area divided by base? What's the area? The magnitude of the cross product. And what's the base? Well, I just find the magnitude of that vector. That is actually a trivial problem. That problem is very simple. So let's apply it to here. I would like you to find the distance. It doesn't matter which point. Let's say from, how about Q to the line passing, oops, can't spell, line passing through P and R. So I have P, I have R, I have Q, and I need this distance. Okay, well, I need two things. I only need two things. I need the magnitude of the cross product. And by the way, it would not have mattered if you did PQ, PR, RP, RQ, QP, Q. It didn't matter which, because we all agreed that the magnitude of the cross product was going to be the same regardless of how I found it. So what's my numerator? I'll call this height. My numerator is going to be, and I'll write it like this, the magnitude of, this is kind of shorthand notation, but it's pretty clear what I'm saying here. The magnitude of that over the magnitude of what? Over the magnitude of PR, which would be that guy. So you don't want to get fancy, you don't want to get clever, that's my answer. What if I had said through, you know, P and Q, then or you know, R and Q, wherever I'm saying here, you're going to find that magnitude of that vector, which is fairly trivial. Okay, you with me so far? So, what's my numerator? Keep losing my eraser. Over here. So my numerator is what? 25 plus 9 plus 64 under the root. My denominator is 1 plus 1 plus 1 under the root. So I think this is what? 34. So root 98 over root 3. That look about right? I don't think 98 has a factor of 3, so I don't think you can reduce it. In the strictest sense, there's only a couple things that are not considered simplified or finished answers with roots. We generally don't leave a fraction under a root, and because a fraction under the root is still the root of a quotient and a quotient of roots. So a lot of people would say, well, you know what, you can't really leave both of them as roots. I don't have a problem with that. Now, it might be practical to multiply top and bottom by root 3. It might be practical. It depends what you're going to use this for. I just asked you for a distance. So at this point, you might just pull out your calculator and give me an approximation, right? Because that's the answer, but do you have a feel of how long that is? Now, we're going to do stuff really soon involving motion. Like we're going to throw an object and say, you know, how fast is it going when it hits the ground? And you're going to get, everything's going to be square roots, and you're going to go, great. And, you know, my answer is the square root of some gargantuan number. And I'll usually say, well, why don't you throw that into your calculator just to see the size of that to make sure your answer actually makes sense. This is the answer. It's not really important that I give a decimal approximation, but if I made a mistake, might the numbers be absurd? Is that possible? One of the things I find people do all the time is they'll say, well, I didn't like that answer. I just didn't like the answer. I'll say, well, did you see an error? No, I just didn't like it. Why? Because the number was either too big or too small. But I say, well, what were you expecting it to be? So if you have an expectation of what you think is reasonable and then your answer is in that realm, then you go, okay, that's all right. When we talk about motion, you know, I'm throwing an object up in the air, or I'm throwing it across the room at a particular speed. For it to be going, you know, supersonic jet when it hits the ground is probably not realistic. For it to actually be going slower when it hits the ground is actually impossible. There are some bad answers, but a lot of times you're going, well, I got this answer. It's going a little faster when it hit the ground. It's not outrageous. I probably should go with it, and you're probably right. A lot of times we don't like our answer, but we don't have a feel of what it should be. So that's why I say that is the answer, but maybe a quick calculation, because when you're looking at, if you could actually draw this in 3D, don't worry about it. But if you were looking at it and going, you know, I would think these are way closer together, or I think they're way farther apart. If my numbers that I was using were really large, is it reasonable that these would be really far apart? If I was using very large numbers, then you would be suspicious of a very small answer, would you? If all my numbers are very small, you would probably be suspicious of a very large answer for the same reason. Okay, so a lot of times we throw out a good answer for no really good reason. I'm just saying, look, unless you see an error, always go with what you said. All right? Are there any questions? Okay, can you,
Isn't any scalar multiple of n the correct answer?
slow down, say again.
Isn't any scalar multiple of n the correct answer to that question? Because
Yes. Any scalar multiple of this would be a vector that is orthogonal to that. I want to go with this one because it's the one I came up with first. But, what if, and this will happen, what if these were all very large numbers, but they were all, let's say all of these were multiples of 100. You might say, you know what, I'd rather use the smaller numbers, and you'd be correct. Next day when we learn how to find equations of planes, that's something we will actually consider. If the numbers I'm using are really, really large, and I know any multiple of this works, then I may choose a smaller multiple. That's something you could do. There would be no reason to alter this answer because it's the first one you came up with, but you are in fact correct. Does everyone understand the question? Any multiple of this, because it would be on the same line. So if I said -1 times this, That's the result I would have gotten if I reversed the cross product, or I simply found different pairs of vectors. So exactly half your answers would have been this, half would have been negative 1 times this. That's why they're both correct. Okay, go ahead and stop filming. Yeah.